Let's get going. So today we will follow on from where we were last time. And so we'll talk again. So remember last time I asked you to forget everything about two fluids moving in a porous medium, and we talk about aqueous transport carried by water. So we'll briefly recap what we talked about last time quickly, and then we'll talk about the end point of our deliberations last time, the advection-dispersion equation, and how we solve that or use solutions for one-dimensional and three-dimensional flows. And so we start. This is where we started last time. We know that if we know Darcy velocities, we can get advective velocities. We can calculate masses transporting through these systems as volume rates of fluid, and mass rates of transport if we know what the solubility is, or the concentrations and the volumetric flow rate. You've already used the idea of these propagation curves for stuff traveling from upstream to downstream and giving residence time distributions. And I guess what we were asking is, how do we quantify this curve? Is it always true that the length traveled is given by the advective velocity times time? Is it always true that the mid point on this curve occurs at that arrival time, or does it differ? We talked about the fact that we have two different kinds of transport. We have diffusion, which is flows under a concentration gradient, and we have transport by advection, which is carried by the bulk motion. We use an analog of a bubble of ink in a beaker carried across the front of the room to mention it, to rationalize it. We talk about the fact that diffusion appears in these systems, but there's also the effect of mechanical dispersion, which is due to mechanical mixing, which looks like diffusion, and therefore you can use the same characterization as diffusion. We describe these different behaviors. We use the conservation equations for diffusion and advection to derive the advection-dispersion equation, which is what exactly this is, which gives us these behaviors if we solve it, and which we will do today, or look at solutions for it. And we characterize the behavior in terms of an upstream boundary condition, flow through the porous medium, and then the residence time distribution curve at the outlet, defining exactly what happens to a receptor at the arrival. And we made the case that you get plug flow if the dispersion is zero. If dispersion is larger than zero, it gets progressively canted over. And if it becomes really large compared to the advection, then it actually doesn't go through the 50% point at the time of arrival. And we talked about the fact that this diffusion that we see, we actually call dispersion, which is due to mechanical mixing. It looks like diffusion if you see it without knowing what the mechanism is by which it's caused, and we can represent it by an effective dispersion coefficient. And that dispersion coefficient is mechanical behavior plus chemical diffusion, and we can put them together. So that's where we kind of left it. So I was going to go back and use something else. I guess I was going to use this to kind of say the same things in detail, exactly the same as we've just kind of summarized. And that is that we have this really a one-dimensional equation, advection-dispersion equation, accumulation upstream. The other part is mass in minus mass out, and that can be due to advection, which is this term here, which is the plug flow that goes along the core, if you like, and dispersion that occurs longitudinally. I guess if it's due to chemical diffusion, then it really is controlled by the concentration gradient. The mixing really isn't controlled by concentration gradient, but kind of looks like that diffusion, and so it gets attached to that. And so the terms that represent this behavior are one for longitudinal dispersion, one's for transverse dispersion, and we can characterize it by these two pieces put together. One is the effective chemical diffusion. Each of these terms are in meters squared per second or per year, length squared over time. And this representation of dispersion has a range. If the velocity is really slow, such as in clays, then diffusion, chemical diffusion, is a number, a big number compared to the advective diffusion, advective transport. And so this term dominates, and so this term drops out, and it just becomes d star, which is just the chemical free phase diffusion in water multiplied by some coefficient omega that represents tortuosity. So we said that this is equal to omega times the actual textbook example or reference text example you get out of a textbook for salt diffusing in water or gasoline dissolving and diffusing in water. This would be the chemical text reference magnitude, and this would be a number between 100th and 0.5, say. And the converse, if the velocity is big, then this number doesn't change and it's really small. Typically this is of the order of actually something like 10 to the minus 9 meters squared per second, I think, of that order. So if this doesn't change, but if this number gets bigger, then this becomes irrelevant, and it's the advective behavior that controls response. So that's the equation that we're working with. We don't care all that much about solving the PDE from first principles, but we do care about knowing what it means, and we talked about both a step input in concentration and a spiked input in concentration. What those look like as they work through a core is that this pulse travels down by plug flow. If dispersion is 0, this is a sharp front, and it arrives down in the residence time distribution again as a sharp arrival. And if progressively the magnitude of dispersion increases, then this becomes canted over. So this is dl getting bigger. And I guess it would also mean this. So that's the basic of the feel for it. And so we can ask again a couple of questions. And we could even add a third question to it. L which I'll explain. So we can ask some questions. So is this value here at the breakthrough? So this is the length that's traveled calculated from the advective velocity multiplied by time. Is this always 50% of the concentration? Is it always halfway? Or could it be that this curve looks like this? Don't know. We don't have any information to say that yet. And if it could look like this at breakthrough, when is this equation not true? If it could look something different. And when it breaks through, is it always present at 100% concentration, or could this concentration be less as it goes downstream? And what are the conditions that allow us to describe that behavior? So that's what the third one is. So these are the geometries that we'd like to look at. This is the 1D geometry that we've been looking at before. This is the 3D geometry. Could be 2D, I suppose, if you look at it in plan view. If this was just an aquifer of just constant thickness and relatively thin thickness that looked like this, then maybe this distribution that we see here is really just two-dimensional rather than being three-dimensional. Right? This is a plan view. You can imagine if it's a really thick reservoir, aquifer, then it would be changing in the vertical direction as well as in the lateral direction and the longitudinal direction. So that would be the difference between 2D, which was this if it's a very thin aquifer, or 3D if it's a very thick one. And so how do we get these relative concentrations and these residence time distributions as they come through the other side? So that's what we're attempting to do. So what we'll do is we'll take this advection-dispersion equation and play around with it. So this is really, I suppose, in at least 2D, because it has behavior in X, but also in Y. So in this geometry here, this would be the X-axis, and this would be the Y-axis. So if you're looking at the plume in those coordinates, then the kind of geometry that you get from this behavior is that this is due to the longitudinal dispersion. This widening of the plume as you go downstream is due to the transverse dispersion existing here. If it's a one-dimensional problem, then this term would drop out and we only have the other two left. So this would drop out if we're only dealing with a 1D problem. So, and it's slightly simpler. And so maybe we'll look first of all at one-dimensional problems. So we're solving this equation first, and then we'll talk about three-dimensional problems later on, where we do need this extra term, or two-dimensional problems. And so let's look at this expression. Again, we're not going to solve it from first principles, but we have to understand exactly why it looks like this and how we can use set equations. So if we throw away this term in the advection-dispersion equation, and we start off without the red terms here, without dividing it, I guess I could get rid of them and then put them back. Might seem counterproductive, but why not? So if we start off with the advection-dispersion equation, what we'd like to do is we want to solve it. And so we'd like to, if we want to solve it, it'd be nice if we had a solution that we can solve for the minimum number of variables that we want to put into it. So we could non-dimensionalize the concentration just by dividing through by whatever the maximum concentration we start off with. So that's pretty straightforward. So if that's the case, then we, instead of a concentration which is in units of mass per unit volume, we now have 1 divided by itself, so it's a non-dimensional number. And so we have one variable that's present within the system. And in the rest of the expression, we have the other parameters that describe it. We have a longitudinal dispersion, we have an advective velocity, we have time, and we have a coordinate dimension. So we can write those out. You never thought you'd see this mentioned again, did you, in your careers? But you write it out in terms of the parameters we have, and so we can use Buckingham pi on it. And so if we use Buckingham pi, what do we have to do? We have a total of 4 variables describing behavior. This is already dimensionless, right? We've already made it dimensionless. So we have 4 variables. We have length, time, but no mass. So we have 2 of our quantities. So 4 minus 2 means that we can describe behavior in terms of two non-dimensional variables in terms of a grouping of these parameters. So what we could do is we could write out this differential equation in terms of its dimensions. And so if we look at the dimensions of this is just 1 over t. Forget the red for now. If we look at the dimensions of this, I've told you that this is meters squared over seconds. So, the terms that come out would be this multiplied by x squared. Don't need to know what the terms are yet. And in this equation, we only have a velocity divided by a length. So what we could do is we could multiply all the terms here by time, each here. We could also multiply this term if we wanted to by 1, which is just velocity over velocity. And it seems kind of futile to do this, but all of a sudden what comes out of this is that we have two-dimensional terms. This is already dimensionless, we don't care. But this is already dimensionless. So this is dimensionless for starters. Velocity times time is a length, divided by a length is nothing. So we have this non-dimensional term which is called a Courant number. In Fedder they call it T sub r, which is actually a pore volume, which means that by the time that you've filled up the pore space of your core by injecting from upstream and it's arrived downstream, you've completely filled up one pore volume. The time taken to do that is this time. So it's given by the advective velocity, the time, and the length of your core. And if you take this term here and multiply by velocity top and bottom, and if you substitute this term into here, the term that remains is going to be this second term here. So this first term is called a pore volume, or after an originator, a Courant number. Courant Institute at New York University, a famous mathematician, which is this, and this is a Peclet number. Must be E, right? Resume has an acute accent on the E's, so I think it has an accent. So this term, 1 over this term is a Peclet number. So those are two terms that we can use. Like all dimensionless numbers, they mean something. You know that Reynolds number is the ratio of inertial to viscous forces. And Peclet number is the ratio of advective flux to dispersive flux. So if advection dominates, then Peclet number is a big number. And so if Peclet is greater than 10, then it means that advection is dominating. And if advection dominates, that means you have a sharp front, like plug flow. So the Peclet number defines that. And the Courant number, actually we won't use it so much in what we do, but the Courant number is actually used to define the time step that you might want to use to solve your equations using a numerical model. The idea is that if a Courant number of 1 means that you've gone from the upstream to the downstream exactly, 1 pore volume. And so in numerical methods, if you use an element to look at solute coming in and going out the other side, if it goes right the way across the element in one time step, then that element hasn't seen that stuff go across it, and so the model will blow up. It won't give you a decent result, and so it's used for that. And so from Buckingham pi, it tells us that we have two dimensionless coefficients that describe behavior. So relative concentration and two other coefficients. Those two other coefficients are Peclet number and the pore volumes, or Courant number. And so it means that we can manipulate this equation in terms of just those variables only, and we can solve it for those variables. And describing what Peclet number is. So if Peclet number is 0, then that means that the velocity is 0, right? If v is 0, then the velocity is 0, and it means it's completely controlled by diffusion. If the Peclet number is greater than 1, I said 10. If it's greater than 1, then the advective velocity, effect of it, bless you, is more important than diffusion, and that component of our dispersion parameter is going to be the advection-dominated part. If it's less than 1, it's going to be chemical diffusion that's going to control behavior. And so based on the Peclet number, actually, we would know exactly what the behavior is. So for a Peclet number of infinity, would be plug flow, and some number smaller than that. And for Peclet numbers less than 1, you'd expect to get this non-sharp flood. And we can expect that. So if we know what the advective velocity is, what dispersion is, and advective velocity, dispersion, and a length scale, how far it's traveled, then we have a way of saying something about what this curve might look at without doing anything with solving these equations. Okay, so that's that, right? So let's figure out whether we can use that to our advantage. So go back to this. Yeah, so you've seen this. You've seen this advection diffusion curve. Won't bother with this. Won't bother with that either. Just saying what we've just said about the value of the Peclet number. What we could do is we could try and solve this equation for this particular geometry. And the behavior would be that we suddenly increase the concentration upstream and keep it at that concentration for all time. And if we do that, we get not a very exciting equation that we won't necessarily solve, but we'd get this long expression. But you note that if we divide both sides through by the concentration that we apply on the upstream, so in other words, this would be the boundary, no concentration, then all of a sudden at time t0, we apply it and it goes up to this. And so this would be 1 by definition. And so it just becomes a term that includes these other two terms. You can see from this is a Peclet number in here. I guess that this term here is kind of a Courant number, C sub r. And I think if you look at these two together, these are a function of both Peclet number, also a function of Peclet number and Courant number that occur here. So there's nothing else in there except from those. So we can describe behavior exactly in terms of these. And so if that's the case, if relative concentration is merely a function of these two parameters, I suppose you could imagine drawing a residence time distribution. So if this is the upstream behavior, there's the boundary condition. This is the behavior in the core. So you'd expect if you looked at the concentration as you go downstream that it would look like this. This would be X. This would be C over C0. if this would be 1, this would be 0. And then if I also draw it at an angle, just so that everything's the same, then this residence time distribution in terms of time and C over C0 would, I suppose, look like this, or this, right? So this would be maybe a Peclet number less than 1, and this might be a Peclet number going to infinity. Big number. And so if we can solve that or substitute values into that equation for Peclet number and the Courant number, and I suppose if this is the core, this Courant number would be TR equals 1, right? It means that you filled a complete pore volume, so the plug flow is now arriving at this point when the Courant number is equal to 1. If the Courant number is only equal to 0.5, it's halfway down the core, and if it hasn't really started yet, if the front is only at this location, that corresponds to a value of this 0. It hasn't started, a time of 0. So it's also t equals 0. T greater than 0, t 2 times greater than 0, right? Since it's double the length. That's all it is. So that's all these mean. So the bottom line is if you plug some numbers in this equation for the Peclet number, and so I suppose if this is your core, and this represents your aquifer, and this is where it's going in, and this is where your well is pumping out, then this would represent L. So you're sampling at this point here, which is L. You know what this material property is. You know what the advective velocity is. And so you can calculate what a Peclet number is. You know your distance downwind. You know where what the advective velocity is. And you don't know the time at which it arrives, but you could calculate that from here, from one pore volume. It would be, so you'd know that this would be equal to 1.0 when this arrives, and so you'd like to know what this time is in real time when it arrives at the downstream end, and you'd like to know the concentration. So if you plug those values for Peclet number and Courant number into this equation, you get a residence time distribution. So the residence time distribution is what we've always drawn on the right-hand side, time versus relative concentration. Not very good. And you'd be able to calculate in terms of, this could be drawn in terms of time or actually pore volumes, either way, you'd end up with a curve like this. So if you plotted this expression, you'd end up with a curve that looks like this. So Peclet number infinity is this. The breakthrough time is when one pore volume goes through. So you've pushed one pore volume, so it's now arrived at this point. Suddenly the concentration goes up to 100%, and that's it. If you're pushing downstream at a lower velocity, it will still take a pore volume to get here, but because dispersion is also spreading things out, something will arrive before a full pore volume arrives, and something will arrive after the pore volume has arrived. So that's kind of curious that it's doing that. So you're getting a finite concentration before those particles of water have arrived. So we should try and figure out exactly what that is. And if you're going at an even smaller Peclet number, then actually what you've done so far isn't correct, right? You've used the residence time distribution, this point here, to decide where it arrives, but actually it arrives at 50% before one pore volume has gone through. And of course that kind of makes sense, because the pore volume, if we plot this term, so if, for instance, the advective velocity is 0 in a clay, then this is saying that the time for it to get to you is going to be infinity. And that's because this advective term is what's controlling this behavior. But we know as the Peclet number gets smaller and smaller, in terms of plotting things in this non-dimensional route, you might expect that the Peclet number, if this is much less than 1, very diffusion dominated, then this arrival is really early compared to the number of pore volumes, because of course if it's not moving, then it would take for infinity to get one pore volume through, and if a diffusive front is moving, it will arrive at some time, it just take a long time to get to the end, and therefore this isn't a proper way of being able to represent it. So that's this behavior. So this curve, if we look at it, if we go back here, I think it, confusingly, it's the end of the last section. This curve here. And so this comes out of Feder, and you see the different coordinates. This is relative concentration of 1. This is one pore volume, which is here. And the lines that we're interested in for the particular boundary conditions are this solid line. This is a constant upstream concentration. And so you see for a Peclet number of infinity, this would be a Peclet number of infinity. And Peclet number Peclet number, just by definition. If a Peclet number is equal to 100, which is what this is, then this is the curve here, the solid curve that comes down here. And I guess you note that it's quite useful that it still goes through, I think it does go through 0.5. Right? This ordinate is essentially 0.5. If the Peclet number is equal to 10, again, which is this, this is the solid curve for that. It doesn't quite, the 0.5 value is not directly on this ordinate, it's in advance of it. And if the Peclet number is equal to 1, then it's this curve here. And of course, this curve is way ahead of that, right? So you filled up the core to half a pore volume. So you'd think that the front would have moved only halfway along the core, but you're getting 50% concentration already after you've done that. Actually, it's 40%, 0.4 of a pore volume. And so the question is, that seems kind of strange. I suppose you could ask yourself why that might be. And a quick diagram would suggest exactly why that would be. If you think about, actually not so, a bit like your, if you imagine having a core with a whole bunch of layers in it, where these are high velocity layers, say sand in clay, then if you think about plug flow of a core going through this, you might think that they would preferentially give you these little advanced fingers of stuff, so that this is concentration equal to 1. This is concentration equals 0. This is concentration of 1. So if you go across this length and you take an average across this section, and I don't know what that average would be, but it'd be 1, 0, plus the weighted average would be 0 here, 1 here, 0 here, 1 here. So maybe the effective concentration might be 0.2. 1 in here, 1 in here, and 0 in all the other parts. So in other words, at this location here, the plug flow front hasn't arrived, but already it's sensing that it has a concentration that's greater than 0. That's exactly what this response is here. This is what the core looks like. What the residence time distribution looks like when it arrives is plug flow, time, concentration, and so this is the behavior. So this point here is exactly this as it goes downstream. So a perfectly rational reason why it should be. And it is that there's been dispersion caused by these different layers, which are real, and that is really what mechanical dispersion is, as we discussed. It's not diffusion anymore. And so that's why you get this early increase in concentration as you go downstream. So that's that. So we can look at different boundary conditions. We won't do that. This is the expression that gives you that solid curve that's printed in that figure from Feder. If you use a constant mass that's put in, or a mass flux that's fed in, you get a slightly different curve, but it's largely the same. You see you can define it in terms of Peclet number and this pore volume term or Courant number, and you end up with the simplifications of that you can use, but we perhaps don't need to use that. Okay, and some other ones. So one-dimensional problems, we can do that. If we have the case that we looked at before, where we have flow within a aquifer, that is it going to look something like this for one possible boundary condition. If we have a source that's constant, so in other words, I suppose a constant source would be that you dig a hole in here, you'd put some dissolvable TCE or some nasty substance in that's at irreducible saturation, and you leave it in here so the water can wash through here and carry it downstream, but it always starts here at the same concentration. Then you'd expect a plume to look like this. I suppose alternatively you can put an injection of putting some fluid in the subsurface that then gets washed downstream. And so if you put it in here and it gets carried downstream, then you might expect the plume to look like actually a rip, dropping a stone in water and having the bulk advection of the water carry that ripple downstream. So this would be putting it in at this point and then having everything washed downstream and downstream. It's getting wider and wider because it's getting dispersed as it goes through the porous medium. And so this would be a constant mass that's injected. So a constant source that's continuously replenished and a constant mass that's injected and then not injected anymore. Done at second 1, but not at second 2, 3, 4, and 5. And so the solution ends up being a relatively straightforward one. You can actually look at it as a cloud migrating downstream. And I suppose, it's drawn here. This is essentially the behavior you'd imagine. So you put it in downstream at time 0. As it moves downstream, then it broadens. It broadens because there's some dispersion in the transverse direction and some dispersion in the longitudinal direction, dl. Likewise here. And at each of these locations, if you look at that profile in cross-section, it would be a mini Gaussian distribution. So this would be this, as well as I can draw it. Obviously, this is concentration on the vertical axis. This would be the radius, I guess, from the center of mass. This is the location of the center of mass. This area here is the mass that's put there. And so this area under here has to be the same. It's just getting, if it's getting wider, it's getting flatter. And so this concentration has to be less. And as you get to this point here, don't know if I can draw it flat enough. Apparently didn't do it fast enough. This would be this. And so this solution is just the bell curve, Gaussian distribution. And as you know, the normal probability distribution is characterized by a magnitude of a mean, right? Which means, I guess, that all the population that's upstream of it and all the population that is downstream of it are actually the mirror image of each other. So if you look at the point where there's the same amount of mass on the upstream side as the downstream side, that defines this point here, which also defines the mean, the definition of the mean. And it also defines a standard deviation. So one standard deviation, I think, is 1 sigma. And isn't that something that contains 66 points? Yes, you're the stat geniuses. What's one standard deviation? What proportion of the population does it carry? Is it 66.7%? Sounds good? Oh, 66.8, all right. Good, that's good. Good, 66.8 then. But 3 standard deviations is 99%. And so this length here that includes 99.7% of this mass is 3 standard deviations. And so the solution to this problem is to take basically the Gaussian distribution, normal probability distribution, allow it in the beaker to go from the skyscraper at time t0 to flatter and flatter and flatter with increasing time, and then carry the beaker downstream. So carrying the beaker downstream is just moving it from here to here, and then looking at what that diffusion is in the beaker, then carrying it the next length to down here, and seeing that it's wider and flatter. And of course, in a beaker of water, that just means that ultimately it's going to look, instead of an ink spot in the middle, it's going to be, all the water is going to be light blue, I guess. And the equation for that is the normal probability distribution, which is this. And all that's changed in this is that it uses these values. So if we use x to be the direction of flow, so this would be the advective velocity. By definition, if that's the principal velocity, then v y advective is equal to v z advective, which is equal to 0, right? So you can have a velocity field, but if you take the principal velocity, the maximum velocity, the orthogonal ones will be 0. And so there's only one velocity in this field. And really what it's doing is it's carrying this mass of fluid downstream and allowing it to spread out as it goes downstream. So in this case then, this would be dispersion. Would it be longitudinal dispersion or transverse dispersion? You can't answer a question with a question. What's go ahead.
It's the constant, the one up there that's constant source. So that spread out is like, that's the fixed case. Like
You're talking about my cartoons.
Yeah.
This one is the concentration is added and it's held constant at all time, so it's the same.
Okay, and then the second one is the continuous mass. Like you drop it in at one point and then you just let it spread out.
Yeah, if you looked at this in cross section, it would look like this. At one time, and then at a later time, it would look like this, and at an even later time, it would look like this. If you did this one with concentration, this is concentration, then it would look like this. And this would be T1, T2 perhaps. No, T0, T1, T2. Yep. So you're answering my question with a question, were you? So here's the answer. And these would each be transverse, right? Because this is your plume. This is X. This is the widening of it. Essentially this length here, right? D transverse and DL. I know I overwrite these things. And so these are the dispersions. This is the mass that's put in at this location here. This is time. And this is just, this would be again DL, T sub L, T sub T, and so these are just the coordinates relative to this migrating location. And so x0 is where is a static location, where it starts, and then it travels downstream from that. And so this relative coordinate is the coordinate you find yourself here. So this would be lowercase x. This value here would be this is x0 plus VT, right? And this would just be X here. So really all it's doing is it's allowing this thing to get bigger as it goes downwind, gradient I guess. And relative to this moving coordinate system, it just sees a Gaussian distribution. If you want to get a solution in this kind of fixed coordinate system, you have to use the initial location, the velocity by which this coordinate system is moving downrange, which is this parameter here, and this is the actual location that you are in this XY coordinate system. So it might be easier to think about it in this way. It certainly is easier to think about it. So if you think about a moving frame of reference, talked about that before, right? If you attach yourself to this center of mass of the plume, you know that you're going down gradient at velocity, advective velocity. You know that in 10 minutes, if you multiply the advective velocity by 10 minutes, you know how far you'll be. And then the plume is merely relative to that coordinate system in uppercase X and Y coordinate system. Much easier way to think about it. But the bottom line is that you can calculate this again to get the concentration and how it changes in space. You'd be able to plot these kind of contours just by using this expression. If it's in Cartesian space, then you need to use this. And if it's relative to the center of mass here, then these are the values that you use to plot. Okay. And so, yeah. And so if you want to get the maximum concentration is always going to be at the middle. The middle of this is always going to be at the values of this, which are 0, 0, and 0. So this is equal to 1, and you're left with this. And so since this concentration changes with the reciprocal of time, it will be largest, this is constant, whatever the mass in kilograms you put in. Time is going to be increasing, so concentration is always going to be decreasing. And so I suppose if you just plotted it in terms of this coordinate system here, so this would be uppercase X, then it would exactly be this. This would be this expression here this would be 1, and then subsequent magnitudes would be t greater than 0, etc. So each one of these would be a normal probability distribution curve. And of course, if these go to be 0, this is just the maximum concentration. So the value by which this concentration would be changing with time would be according to this. And so you just have to realize that that is as it goes down gradient and looks progressively like each of these. Okay. And so the utility of doing this, perhaps we don't care to calculate this complicated expression. It's more useful to us to understand what it means. But if we know always that at the limits of this length here will be equivalent to 3 sigma, 3 standard deviations on either side of the mean. And so if we know what this distribution looks like, we can calculate what this length is. If we know what that length is, then we have a chance of being able to calculate what these dispersion coefficients were if we want to be able to back calculate that from our system. So we know that this length of 3 standard deviations is equal to not cube root, but 3 times 2 times this would be longitudinal dispersion times time. I guess that's the same expression here, less ambiguous. This isn't a cube root, it's 3 times the square root, which is this. And so if we know what this length is, we can relate that to this very simple equation. So this is a length, essentially, that we can measure in the field. Presumably you can measure the half length of this distribution if you knew how to be able to look into the soil and see what the exterior contour of this concentration was. You'd have a length. And if you have a length, and if you know when that length is recorded, time 0, time 1, or time 2, so you'd know this value here, then you could calculate what this dispersion coefficient would be. Alternatively, if you have a value of this, and you know how long the plume's been traveling downstream, you could calculate how big the plume is. So you could calculate the exterior contour of this. and that might be useful to us. And I'm not sure whether we'll, I wasn't going to do it today, but we'll do this later on. So this is exactly that calculation. So you dig a hole, you inject some mass of fluid in it, and you allow it to get carried downstream. And so this was in a sand aquifer in Ontario, in Borden. And so if you could think about putting little capillary tubes in it and then sucking the fluid out at a whole bunch of physical different locations, you could get a contour map of what the plume looked like. So at one day it looks like this. 85 days, if you know what the advective velocity is. So if you knew, for instance, what the contours of hydraulic head were, then you'd know that the velocity, Darcy velocity or advective velocity for that is in this direction. So instead of looking over here to see where the plume went, you'd know you'd have to look in this direction. And if you knew what the gradient was, you could calculate the advective velocity as being the Darcy velocity divided by porosity, which is equal to hydraulic conductivity over porosity times the change in head with length. And this would be x, of course. This would be the x direction. And so if you know what the head gradient is, and if you know what the hydraulic conductivity is, and you know what the porosity is, you know what the advective velocity is. If you know the advective velocity, then advective velocity is equal to length over time. And if you rearrange that to being multiply both sides by time. So if you know the advective velocity and you know 85 days, then you know a length. So you know where to start looking for your pin cushion. And then you take the assay of that. You repeat it after a year and a third, and you repeat it after almost 2 years, and you get this behavior. And so the bottom line is, at this point here, you have a length. I'm doing much more than I planned to do today, but we'll do this again. What's this length? This length is equal to 5 meters. You know that 3 standard deviations is equal to 3 times 2 dLt square root. You know that 3 standard deviations is equal to 5 meters. You know that time is equal to 85 days for this. I think that's what it says. And so you can calculate longitudinal dispersivity, as long as you use the right units. I guess if you use the units here, you'd get dl in terms of meters squared per day. Could be legit units. It's certainly dimensionally homogeneous, this equation. So you just have to be consistent in your units of length and time. And so if you do that, so you don't need to solve that complex Gaussian probability distribution function. You just need to know this one outcome from it to calculate the longitudinal dispersion. And of course, if you wanted to calculate the transverse dispersion, this would be the length that you'd use to calculate longitudinal. This would be the length that you'd use to calculate transverse. Same time, but it'd be a different length. Not much different, but certainly after a year and a quarter, and certainly after almost 2 years, then the longitudinal dispersion is much greater than the transverse dispersion. So you'd expect the magnitudes to come out of this to be different values in some form of ratio as a square root of this. Okay, so I think we're right up at the witching hour. So that's where we're going. So advection-dispersion equation, some of the things that we took for granted was that we get plug flow and the arrival time is exactly equal to the length it travels, governed by the advective velocity and the time. Seemed to be a useful thing for us to assume, but it doesn't turn out to be true, especially for low Peclet numbers. A Peclet number is a number that we can calculate if we know the advective velocity and the dispersion. So we can always calculate it for our aquifer if we know those parameters. And then we can use these one-dimensional solutions. We can use the actual equation itself, or we can use what the equation looks like in terms of the arrival at a downstream compliance location. These are the residence time distributions for the one-dimensional problem. This is the slightly complex expression for it, both in the core and also the residence time distribution. If you want to get what it looked like in the core, you just use different numbers of L and therefore different numbers of Peclet number in this. If you want to know what the residence time distribution is, you just use a constant value of L and you'd use different numbers of the pore volume. You change that number from 0.8, 0.9, 1, 1.1, 1.2 and see what the true arrival times were and the right concentrations. And if you have a problem where you have a three-dimensional behavior, then again we get kind of a complicated expression, but it's really quite simple if you think about it in terms of the probability distribution function just being carried downstream. It'd be the same way as smoke, a puff of smoke from a smokestack goes downstream as it gets carried by the air. Turbulence mixes it up and it gets bigger and bigger and lower concentration as it goes downrange. If we think of it in terms of this attaching ourselves to the moving coordinate system, then it becomes a very simple equation. The center of that mass becomes x, y, z, 0, uppercase x, y, z. And the concentration then is a function of the constant mass that's put into the system, diminishing in time as it spreads out. And we can calculate what that is. And if we think of the idea that it's a normal probability distribution and the span of that is equal to 3 times the standard deviation, then we can simply use this equation to do what we just did to calculate what the dispersion coefficient is, if that's useful to us. Or if we know what the dispersion coefficient is, we could calculate how big the plume is at time 2 years. That might be a more useful thing to us to do. So if we know what DL is, we can calculate what the length is. And so that's probably more useful to us. So that's where we're going. So next time, we'll talk a bit more about this. We'll talk about what experiments we can do in situ to be able to figure out exactly what that dispersion coefficient is. And actually, we'll find out that, well, I won't spoil the surprise. Let's leave it for next time. Yeah, you can't wait. Bated breath. Great. That's it. I know we're right up to the hour. All right?